Welcome back. Today we are exploring water quality. Did you know water can harm us? So let's dive in to learn more about water quality measures to protect ourselves. First, let's talk about the danger of contaminated water. Did you know that unsafe water can harm you, or in extreme case can be deadly? It is true. Many waterborne diseases such as cholera and typhoid are caused by ingesting water that's been contaminated with harmful bacteria and viruses. So, ensuring the safety of our water supply system is crucial for protecting public health. Okay, here what we will cover. Water quality concept. We'll learn why unsafe water can be dangerous and what makes water quality good or bad. Also, we'll discover the rules and guidelines that ensure our water is safe to drink. We'll see why these standards are crucial for keeping us healthy. After that, we'll explore the different factors that affect water quality, known as parameters. Using basic chemistry and math, we'll learn how to calculate these parameters, focusing on the most important ones. Then we'll discuss water hardness and why some places cannot make soap foam like others. We'll uncover the mystery of water hardness, why it matters, and how to measure it. Also, we'll find out how we can collect water samples, whether in the field or in the lab, and how we can monitor and assess water quality. Finally, we'll talk about the water safety plan, a concept from the WHO. We'll learn why it is essential for both developed and developing countries. Let's dive in and explore the fascinating world of water quality together. Water quality is about the safety of water. It's like making sure that water we drink, cook, and bath will not make us sick. Indeed, there are several factors influencing water quality, such as natural activity. Things like rainfall and soil or rock types can affect water quality naturally. It's like when rain passes dirt into a river, making the water dirty. Industrial activity can also impact water quality. Factories, for example, might release chemicals or waste into rivers and lakes, making the water unsafe. The characteristic of water quality can determine if it's safe for us to use. If water isn't clean, it can make us sick or cause problems. That's why we need to take steps to ensure our water quality is safe. We can do this by adopting various mitigation measures. Quality standards and guidelines are like rules that tell us how clean water should be to keep us safe. They are set by international organizations like the United Nations Environmental Protection Agency and European Union as well. Of course, WHO considered as a leading organization in development of standard guidelines in water quality sector at global level. WHO is part of the UN umbrella. But why standard matters? Actually, protecting health. Standards ensure that the water we drink, cook, and bath is safe and will not make us sick. They also protect the environment by preventing pollution and preserving ecosystem. Also, standards help ensure that water quality is consistent across different places and over time. Surely, all national and international standards are merely focusing on setting allowable levels of contaminants in water to protect public health. Today we are exploring the three key parameters that help us understand water quality. Physical parameters consider all physical aspects which give us clues about water quality, while chemical parameters focus on chemical composition like dissolved substances. These parameters tell us what's in the water. Now, microbiological parameters or microorganisms like bacteria and viruses indicate water safety. So, by examining these parameters, we ensure our water is safe and clean for everyday use. Let's start by exploring the physical aspect of water quality, the characteristic we can observe with our senses. This aspect like temperature, clarity of water or turbidity, and color or pH. All these aspects we really can get the sense of it and feel it by ourselves without the need of test. Surely temperature, turbidity, color, pH, and taste are all physical parameters. For example, temperature. Temperature is like the mood of the water. It can be warm or cool. Think of a swimming pool on hot weather. How does the water feel? Temperature affects aquatic life and can indicate changes in the environment. Turbidity is also about clarity. It tells us how clear or cloudy the water is. Imagine looking into a glass of water. Can you see through it easily or it's cloudy? Turbidity can be influenced by soil erosion, pollutant, or natural particles in the water. Also, changes in color can signal contamination or the presence of organic matter. pH is like the personality of the water. It tells us if it's acidic, neutral, or basic. pH affects the ability of water to dissolve minerals and can impact aquatic ecosystems. Indeed, we can say simply physical parameters is all about taste, color, and smell. By understanding these physical parameters, we gain valuable insight into the health and condition of our water sources. Today we are uncovering the mystery of pH, the key to decoding water acidity or alkalinity. Ever wondered why we use logarithm scale in pH? Let's simplify the concept. Logarithm compress a wide range of value into a manageable scale, making it easier to interpret or compare. So the formula said to us pH equal negative logarithm H plus, while H plus means simply the concentration of the hydrogen ions in the water. Imagine you have a cup of water. Basically, it should have a balance of hydrogen ions and hydroxide ions, creating neutral water. But how do we express the concentration of hydrogen ions? It's often very small number like 0.00001. Writing all those zeros is impractical. So we use logarithm scale instead of writing a lots of zero. We simply say instead of 0.00001, a pH equals 7. Indicate neutrality. But be aware, higher concentration of hydrogen, when we put it in the logarithm scale, it will give us lower pH number. For example, imagine we have a cup of water that consists of high number of hydrogen ions, say 0.1 mole per liter. Yes, 0.1 mole per liter in the word of ions is high number compared to 0.001, right? So logarithm of 0.1 give us a pH equal 1. That's why we say it acidic. It has a high number of hydrogen ions, while logarithm of 0.00001 or 10 to the power negative 8 shows a lower concentration rate, give us high pH value equal to 8. That's we call it basic. So logarithms simplify the complex of word of pH, enabling us to grasp the balance of acidity or basicity in water more easily. Remember, basic and alkaline are different words meaning the same things. Imagine water molecules are like a big city with hydrogen ions, and the workers, more workers, resulting in a lower pH, indicating acidic condition. Conversely, fewer workers, leading to a high pH number, signify basic conditions. Think of water as a taste test. If it tastes sour like lemon, it's acidic. If it tastes bitter like soap, it's basic. pH measures this acidity or basicity. The scale goes from 0 to 14. A pH of 7 is neutral, like pure water. Acidic substances have pH value less than 7. Think of lemon, fruits, or normal acids. Basic substances have pH value greater than 7. Imagine baking soda or soap. For instance, lemon juice has a pH around 2, making it acidic. On the other hand, baking soda solution has a pH of around 9, making it basic. To visualize, think of litmus paper. It turns red in acidic solution and blue in basic solution. That's why we see different colors when we simply write or search for the word pH in our Google search engine. Now let's shed the light on turbidity and its mysterious unit, NTU. Ever wondered where it comes from? Turbidity is like the cloudiness of water, caused by suspended particles. Imagine trying to see through fog. It's like that, but in water. Now NTU stands for nephelometric turbidity unit. But what does that mean? It's all about light. NTU measures how much light gets scattered or absorbed by particles in water. Think of it as shining a flashlight through a fog. The more particles in the fog, the less light you see. NTU help us gauge water clarity. Clear water has low NTU values, while cloudy water has high values. This matters because turbidity can affect aquatic life, drinking water quality, and even the efficiency of water treatment processes. So make sure to make our water turbidity lower than 5 NTU to be safe. Thankfully, there are several devices now that can assess water turbidity in just a second. Now let's shift to the chemical water parameter, unlocking the secrets of its ingredients. Chemical parameters include heavy metals and minerals. Heavy metals can sneak into water source through industrial waste or natural deposits, posing health risks to human and aquatic life. Now let's talk about nitrogen and phosphorus. They are like the nutrients of aquatic ecosystems promoting plant growth. But too much of good thing can be harmful. Excessive nitrogen and phosphorus, often from fertilizers or wastewater, can lead harmful algal blooms and water pollution. Finally, we have organic pollutants. These are like the unwanted guests at the party, pesticides and other chemicals. They can enter waterways through runoff or wastewater, contaminating water and harming both human health and the environment. So by understanding these chemical parameters, heavy metals, minerals, nitrogen and phosphorus, and organic pollutants, we can gain insight into water quality and can take steps to protect our precious water resources for generations to come. A good example of heavy metal substance like lead, mercury, and cadmium. Now let's look on this example of a green water bodies. This color appears from the high concentration of nitrogen and phosphorus. These elements promote the growth of algal bloom. Wait, there is even more. Here are some additional sources of contamination like wastewater and agricultural activities. Now time for real life measurement. Did you hear about total suspended solid? Well, it's a simple way to estimate water quality parameters at field level. We simply call it TSS. This parameter includes large particles like sand, gravel, and sediments. Also, organic pollutant and microplastic particles are main contributors. Let's unlock the mystery of calculating TSS, the solid particles suspended in water, thanks to the power of math. TSS represents the mass of solid particles suspended in water, like tiny particles floating in a glass of water. To determine TSS, we use a simple formula. Divide the weight of suspended solids by the sample volume. To do this, we need only a filter to measure TSS. But also, it's important to know the limits. TSS less than 10 mg per liter is considered slow, indicating relatively clear water. On the other hand, TSS greater than 1000 mg per liter is considered high, indicating heavily turbid water. Let's uncover the hidden elements in water. Total dissolved solid, TDS. That escape from our eyes. TDS comprise minerals, heavy metals, and salts dissolved in water like hidden treasures beneath the surface. Imagine water as a magic liquid containing calcium for strength, iron for resilience, and sodium chloride for flavor. These elements dissolve into water, becoming part of its spirit, but remaining invisible to our eye. Understanding TDS is vital for assessing water quality. Elevated TDS level can affect taste, health, and the performance of water treatment processes. So, by recognizing the significance of TDS, we can ensure that our water remains pure and safe with essential minerals for our well-being. TDS measures the concentration of all dissolved substances in water. TDS can be estimated by weighting evaporated solid over sample volume. Indeed, this can be done through a common laboratory technique for estimating total dissolved solid. The idea is simple. Just carefully evaporate a measured volume of water sample using controlled heating. As the water evaporates, any dissolved solid in the water remains behind, becoming more concentrated in the remaining liquid. Then we can easily weight the remaining solids. TDS limit is quite different. So TDS less than 100 mg per liter considered low, while TDS equal to 1000 mg per liter considered very high. Let's explore the hidden world of dissolved oxygen in water. Dissolved oxygen is essential for aquatic life, supporting respiration just like air for us. The formula may seem complex, but it's surprisingly simple. It's a ratio between atmospheric pressure, water vapor pressure, and oxygen saturation. Imagine it's like a recipe, combining ingredients in the right proportion to create the perfect environment for aquatic organisms to thrive. Monitoring dissolved oxygen level is crucial. So low levels should be less than 5 mg per liter, which can indicate poor water quality, while high level, which is greater than 8 mg per liter, are signs of healthy aquatic ecosystems. Now, let's look on the power of water's currents, conductivity. Conductivity measures water ability to conduct electrical current like a river flowing with energy. It's all about the dissolved ions in water, charged particles that carry the current. We use conductivity units called microsiemens per centimeter to quantify this ability. A low conductivity, less than 100 microsiemens per centimeter, suggests relatively pure water like a serene stream trickling through the forest. But a high conductivity, it could be greater than 1000 microsiemens per centimeter, indicate elevated levels of dissolved ions, which is signal potential contamination or mineralizations. Let's look deeper on the unit. The term micro means very small, so microsiemens are just tiny units used to express conductivity. Think of it as a way to measure how fast the electricity can flow through the water. Let's delve into the realm of chemical oxygen demand, COD, a measure of the oxygen required to chemically oxidize matter in water. COD quantifies the amount of oxygen needed to break down organic and inorganic substances in water through chemical processes, or chemical oxidation. It's like a battle between oxygen and pollutants, where oxygen acts as a superhero fighting to purity and purify the water. We express COD in units of milligram per liter, representing the amount of oxygen consumed per liter of water. A low COD less than 10 mg per liter suggests minimal pollution. Conversely, a high COD greater than 100 mg per liter indicates significant pollution. But wait, why oxygen oxidized? Let's put it more simply. Imagine we throw organic fruits mixed with water in a place. After a while, the smell will be bad due to the decay of the organic matter. Organic matter is all about series of complex carbons, and when carbons find oxygen, they make relationships and bring CO2. That's why organic matter reduced when find oxygen. Let's explore the role of chlorine residual, a crucial factor in maintaining water safety post-disinfection. Chlorine residual represent the remaining chlorine concentration in water after the disinfection process. Imagine chlorine as a fighter against harmful pathogens to keep our water safe. Even after the bottle, there is need of a tiny chlorine remain, ensuring ongoing protection. We measure chlorine residual in milligram per liter, revealing the concentration of chlorine is still present in water. Acceptable level of chlorine residual are typically less than 1 milligram per liter, signify effective disinfection while maintaining water quality. However, chlorine residual exceeding 5 mg per liter indicate overchlorination, potentially leading to taste issues as well as health concerns. Let's unravel the magic of pool testing, a simple and effective method for measuring pH and residual chlorine level in water. A pool testers assess water quality easily by adding a few drops of a testing agent to the water sample. We notice a color change in the water, then we compare the color change with the existing color on the test, allowing us to determine both the pH and residual chlorine. With pool testers, anyone can become a water quality tester, ensuring that water remains clean and clear for all. Remember, it's not only used in a swimming pool, but also can be effective in any water system, particularly in development setting. Let's look into the world of microbiological parameter, a hidden danger in water, bacteria. Let's shine a light on bacteria, an invisible microorganism that can live with the water, posing risk on human health. Bacteria are tiny microorganisms that can inhabit water sources, some of which are harmless, while others can cause illnesses. Protozoa are single-celled organisms that inhabit water, some of which are harmless, while others also can pose risk to human health. Think of protozoa as a microscopic hunters navigating through water in search of prey and food. Viruses, now we will talk about very, very tiny organisms. Viruses are a microscopic pathogens that can inhabit water. also some of which can cause severe illnesses in humans. Imagine water as a vast ocean with viruses as the unseen predators waiting to infect unsuspected victims who come into contact with contaminated water. Don't worry, we will talk about each organism in details in next lesson. Now we can explore the diverse world of bacteria, essential indicators of water quality. Bacteria are microscopic organisms that play a vital role in water ecosystem, with some types serving as indicators of contamination. Among the main types of bacteria are coliform bacteria, fecal coliform bacteria, and E. coli, each with its own significance in assessing water safety. Coliform bacteria are a group of bacteria found inside the stomach of animals and humans. These bacteria are commonly used as indicators of fecal contamination in water. Fecal coliform bacteria are a subset of coliform bacteria that specifically originate from the intensities of warm-blooded animals, serving as a more specific indicators of fecal contamination. E. coli is a specific type of fecal coliform bacteria commonly associated with human and animal waste, and its presence in water indicate potential fecal contamination and the risk of waterborne illnesses. So, why coliform bacteria? In the vast microbial world of water, it's impractical to test for every type of bacteria. That's where indicators like coliform bacteria come in. Coliform bacteria serves as reliable indicators of fecal contamination in water, making them valuable tools for assessing water safety. So, when we detect E. coli, a specific type of coliform bacteria in water, it's a clear sign and indicator that fecal contamination is present. Okay, how to count bacteria in water? Well, we have several laboratory techniques, but the most common methods are two. One is called the most probable number, or MPN, while the second technique called membrane filtration method. Indeed, both had its own advantages and disadvantages. MPN, or most probable number, is a statistical technique used to estimate the concentration of bacteria in water. So the procedure as follows. First, we prepare a series of dilution of the water sample, creating a range of concentrations. Next, we incubate multiple tubes of growth medium with the diluted samples, providing bacteria with the ideal condition to grow. After an incubation period, we observe the tubes for signs of bacteria growth, such as turbidity or gas production. Using statistical tables or software, we can determine the most probable number of bacteria present based on the pattern of positive and negative results. Here is an example of table. As we can see, if no tube present any change, then we can say the number of bacteria is less than 2.2 per 100 milliliter. While if the 6 tubes with change color, we can say it's above 16 mpn per 100 milliliters. Membrane filtration is a sophisticated process that involves passing water through a fine filter, trapping microorganisms along the way. The procedure as follows. First, we have to ensure all tools are clean by heating process. Then we prepare a new membrane filter with pores so small that only microorganisms can be captured. So, here we can see how the filter might look like. Now, next we can carefully filter a known volume of water through the membrane, effectively concentrated by bacteria present. The membrane is then transferred to a nutrient-rich growth medium, providing the perfect environment for bacteria to grow and form visible colonies. After an incubation period, we count the colonies on the membrane, allowing us to estimate the concentration of bacteria in the original water sample. Now let's explore the concept of water hardness, an essential characteristic influenced by dissolved minerals such as calcium and magnesium ions. Water hardness refers as the concentration of dissolved minerals, particularly calcium and magnesium ions in water. These minerals are essential for various biological processes, but excessive levels can lead to issues like precipitation in pipes. There are two main types of water hardness: permanent hardness and temporary hardness. Okay, water hardness prevents soap from forming effectively, resulting in reducing cleaning efficiency and reduced on surface. Furthermore, it can lead to the formation of insoluble precipitates, which can clog pipes and reduce the lifespan of water using applicants. permanent hardness caused by calcium, magnesium sulfate, and chloride salts cannot be removed by boiling, while temporary hardness caused by calcium and magnesium and can be treated by boiling, as it converts the bicarbonate ions into insoluble carbonates. Hardness calculation revolve around determining the concentration of calcium ions, which are primary contributors to water hardness. Calcium ions, along with magnesium ions, are key players in forming minerals deposits and affecting water quality. So the procedure as follows. To calculate water hardness, we start by measuring the concentration of calcium ions present in water sample. Next, we find the calcium carbonate equivalent factor, a value that represents the equivalent amount of calcium carbonate in water sample. Finally, we multiply the concentration of calcium ions by the calcium carbonate equivalent factor to determine the overall water hardness. To understand the equivalent factors, imagine we want to make cookies and you want to know how much sweetness in a plate full of cookies. You cannot directly measure with sweetness, but you can measure the amount of sugar. The amount of sugar is like calcium ions in water. Different sugars have different sweetness powers. So regular sugar, like the calcium for example, might have a sweetness power of 1, I mean equivalent factor of 1, while brown sugar like magnesium might be less sweet with a power of 0.5, I mean equivalent factor of 0.5. In water hardness, we use calcium carbonate equivalent factor as a common method to simplify the process. Let's have an example. Water sample has calcium carbonate, water sample has calcium concentration 80 mg per liter and magnesium ion concentration of 0 mg per liter. So calcium hardness equal calcium concentration times the calcium carbonate equivalent factor. So here we can say that sugar concentration, I mean calcium concentration times power of sweetness, I mean here calcium carbonate equivalent factor. So the equivalent factor can be found from standard reference, which is 2.5. So CH equal 80 mg per liter times 2.5, then it will end up with 200 mg per liter as calcium carbonate. So total hardness equal 0 plus 200, which is finally the total hardness equal to 200 mg per liter as calcium carbonate. We have seen some great starting points, but here we can explore several methods for collecting water samples, each offering unique advantages and applications. Grab sampling involves collecting water samples directly from body of water using a grab sampler, a tool resembling a large spoon. This method allows for targeting samples of specific depth and locations within the water body, providing representative samples for analysis. Simply, it's like you want to taste a single cup of popcorn from a big plate to see if it's properly seasoned. The second option is composite sampling, involves combining multiple individual samples taken at different times or locations to create single composite sample. It's like checking the water temperature in your house throughout the day by taking reading at different times, morning, afternoon, evening, and averaging them. By blending samples over a period of time or across various points, composite samplings provide a more comprehensive overview of water quality. Now, point source sampling focus on collecting samples from specific discharge points or source of pollution such as industrial outfalls or wastewater treatment plants. This targeted approach enables the identification and assessment of potential sources of contamination, facilitating efficient pollution control measures. Also, there are several ways to monitor water quality, and we can do it by monitoring stations, GIS, and remote sensing, or frequent water testing. By doing this, we can ensure safe, clean water supply system. Interestingly, we can assess water quality simply by obtaining data from the field, conducting data about water quality parameters, and monitor the water supply system to ensure better reporting mechanism. Let's embark on a journey to ensure water safety plan through the implementation of this proactive approach to mitigate the risk associated with poor water quality. The first step in developing a water safety plan is identification of potential hazards in the region that could compromise water quality. This involves assessing sources of contamination and understanding their impact on water sources. Next, a thorough risk assessment is conducted, evaluating the likelihood of severity. By ranking risk based on this potential impact, priorities are established for effective risk management. Then, specific control measures are then defined to manage and mitigate the identified risk. These measures may include infrastructure upgrade, monitoring protocols, and regulatory enforcement. Establishing a standardized operating procedure ensures consistency and reliable in water management practice. So, clear guidelines are set for water treatment, distribution, and emergency response protocols. Also, communication and training. Effective communication channels are established to disseminate information and coordinate response efforts. Adequate training programs are implemented to equip personnel with the knowledge and skills necessary to uphold water quality standards. Also, we have record keeping. Comprehensive record keeping is essential for tracking and documenting all aspects of water quality management. Accurate records facilitate traceability and accountability in the field of audits. Emergency response and preparedness. Robust emergency response plans are developed to address unforeseen events or water quality emergencies. Preparedness measures ensure timely and effective response to minimize the impact of public health. By implementing water safety plan encompasses hazard identification, risk assessment, control measures, standard operation procedure or SOPs, communication, training, record keeping, and emergency preparedness, we can proactively safeguard water quality and protect public health. Surely, there are so many of water quality testers or devices available in the market. Some are quite sophisticated, that includes a combination of tools to measure main parameters and can be used in both field and lab. But while there's water quality devices are simpler, like pool tester, which consider cheap and can bring very quick assessment for only very specific parameters such as pH or chlorine residual. As we conclude our journey through water quality management, let's take a moment to explore the standards set by the WHO as a guiding light for ensuring water safety. The WHO established comprehensive guidelines for various parameters to ensure the safety and quality of drinking water worldwide. These standards serve as a benchmark for government, organizations, and communities to assess and manage water quality. So here are some key parameters and their respective WHO standards. Total dissolved solid should be less than 600 mg per liter. Hardness should be less than 500 mg per liter. pH should be in the range between 6.5 to 8.5. Turbidity should be less than 5 NTU. Total chlorine should be 0 colonies per 100 milliliters for drinking water. So these values represent the maximum allowable limits for each parameter to maintain safe drinking water. See you next time, and let's continue our mission to ensure clean and safe water for all.